Get some people.
I am. You have some people. Right. Oh, two of you. Stereo.
All right. Yeah, very confusing. Hello, everyone. So welcome to Deeper Talks, the Surf seminar series. Today we are having Derek Ellsworth, but as usual, we will have a Q&A session following the presentation. So please use the question section below. Use the Q&A button, and then you can type in your questions. So this talk will also be recorded and available to view on the website. So that's institute.surf/deeper-talks, also on YouTube and on Vimeo. With that, I want to introduce our speaker, Derek Ellsworth. He is G. Albert Shoemaker Chair, Professor of Energy and Mineral Engineering and Geosciences, and co-director of the Center for Geomechanics, Geofluids, and Geohazards at Penn State University. His interests are in the areas of computational mechanics, rock mechanics, and the mechanical and transport characteristics of fractured rocks, with application to geothermal energy, the deep geological sequestration of radioactive wastes and of CO2, unconventional hydrocarbons, including coal gas, tight gas shales, and hydrates, and instability and eruption dynamics of volcanoes. Very broad spectrum. All right, so today he's going to talk about scaling permeability, evolution driven by seismicity. So without any further ado, Derek, go ahead.
Great, Marcus. Thanks so much. I just set my timer for 30 minutes so I don't overstep. Let me share my screen. Hello. So can everyone see the screen, Marcus? Someone give me some feedback.
Yeah.
It's okay. Yeah, great. Well, great to be here. I toiled on what was NUSL and then DUSL, maybe from 20 years ago in the early 2000s, 2002 onwards, when this was just an initial idea. This is a picture taken in around 2009 at the 4850 level. With the only person I recognize on there is Brian Mayu, who's at Barnard College in Columbia, the guy on the left-hand side. And I realized that the audience might be much more general than usual for me. And so rather than the scaling of permeability as an idea, another label for the talk would be using SURF and other demonstration projects to scale permeability evolution driven by seismicity. And so that's the topic for today. And so the relevance of this is related to being able to extract fuels and energy from the subsurface, or to contain energy waste such as CO2 for CO2 sequestration, recover geothermal heat, or recover hydrocarbons from the subsurface. Pretty much in all of those cases, you need to be able to create permeability to allow you to pull those fluids, either energy-laden fluids with heat or fuels out of the subsurface, and being able to understand the degree to which you've managed to create permeability controls the efficiency of your operation. Of course, in the other side of the coin is for CO2 sequestration, you would like to keep them in place. And so you'd like to be able to understand that you're not creating permeability by injecting these fluids. So the utility of doing this is quite clear, I think, for these subsurface projects. So why SURF? SURF is something that had its genesis maybe in the early 2000s through a variety of steps from the biology, geoscience, engineering side, BGE. It started off with an Earth Lab report sponsored by NSF, some other work that ended up in about 2010 with a relatively clear picture of what the BGE activities would be, shown on the right-hand side, with a variety of proposed facilities for the underground activities. So it's different from the physics in that the physics are interested really only in the shielding, the fact that there's low radiation at depth. And all of the BGE activities are interested in the very specific strata and their characteristics, stresses at depth, and their mineralogical characteristics, and their structure in terms of fractures and faults within. So that's the difference between those interests of those two communities. In the pathway towards SURF, there was a National Academy review in December of 2010. From this is one of the slides that was used there. What happened was that the National Science Board of the National Science Foundation decided that NSF was not a good vehicle for funding the nascent DUSEL, and because the MREFC spending, which has to be approved by Congress, was becoming too heavy to bear, and they transferred it to DOE. The physics community had a home at DOE, but the geo community had less of a home, as it turned out. And so some of the activities that were planned really didn't go ahead. Some of the activities that could be done at SURF, this was a slide that was made for maybe for 2021, when we had an online SURF meeting to look at questions that could be answered in an underground research lab at SURF. And this is just one slide of one set of prospects, and those are looking at small earthquakes and understanding the nucleation and rupture of earthquakes, very small earthquakes. This was involved in the original DUSEL proposal. The physicists were very unnerved by this, having earthquakes in a place where you have multiple detector tubes around these Cherenkov detectors in these caverns. But these events that we're talking about really are very small, and it's turned out that doing such experiments on underground facilities have shown that you can have indeed very small magnitude earthquakes. One such event was this experiment done in a former underground ballistic missile silo in France, which is now been decommissioned. And it was to exactly do that, to reactivate a fault by pumping fluids in it and measure the characteristics in terms of what happens within that fault as you reactivate it. And those were the kinds of activities that were proposed also for SURF, which DUSEL, which became SURF. Two activities that have already been conducted there are the Kismet project, I think at the 4850 level, and also the EGS collaboration, which were, Kismet was to look at earthquakes that are generated by injecting fluids into the subsurface for the kinds of projects we looked at before, CO2 sequestration and geothermal energy, and to try and minimize induced seismicity from those. And the EGS collab was one project that was developed to look at the possibility to make a connection between an injection borehole and a recovery borehole, shown on the right-hand side in red and green, and to see what the mechanics were in making that connection, flowing fluids through them to recover the heat that was in situ, which isn't very hot, of course, at SURF, but you can understand the processes which are involved in this. And so the idea is that you can be at 1,500 meters deep, the 4850 level, have the same kind of stresses that you'd have in a real system at those depths, but maybe be only 20 meters from the stimulated zone that you're recording. And so it's quite easy to run relatively inexpensive experiments with good resolution of seismic data from those as you do it. So that's kind of the big picture background as we step through this. So I'll try and make the case for why we want to link permeability to seismicity. I'll talk a little bit about the sizes of events and how they scale with injection volumes. I'll then talk about linking seismicity to permeability from laboratory experiments. But the final part in linking micro earthquakes to permeability evolution, I guess, is really the focus of this, because that is concentrates on using surf. The evidence that exists for earthquakes being linked to permeability changes are a number of observations. These are observations of earth tides generating fluid pressures in wells. And if you measure the lag between the earth tide, the loading by the moon as it navigates around the earth, the pressure distribution, the lag between the maximum effect of the earth tides and the maximum pressure generated by those earth tides, the lag gives you some measure of permeability. And so this was some observations that far-field earthquakes, the timing of them given by these dashed lines, caused changes in permeability that were observable in this aquifer through some boreholes. And with the arrival of each of these far-field earthquakes, distant earthquakes, permeability would jump up and decay slowly over time. Other observations are looking at the seismicity that results in faults, using AI to get many more pics and therefore many more observations of individual earthquakes, and from maybe increasing tenfold by using machine learning the number of events that you can see, using that to look at the progression of fluid pulses moving along faults, being observable in the seismic field, and linking that maybe to migration of fluids in the crust, but maybe, but not necessarily, changes in permeability that result from that. If we think that earthquakes would generate porosity and therefore permeability in the crust, we know that earthquakes occur continuously, and we know that permeability doesn't always increase. It's at some stasis within the crust. And so there have been mechanisms by which it heals and seals. And you can also look at those in the laboratory as well. I won't say very much about that. But the net effect is that if you look at the distribution of permeability in the crust, given by this section here, it has this steep drop-off in terms of log permeabilities. So it reaches some very small value. It's large, shallow in the crust, is very small as you get deeper into depth. And the two red bars that are shown here are just illustrating the fact that if you look at the in situ permeability, maybe of the order of a microdarcy, 10 to the minus 18 meters squared, to make it a viable geothermal reservoir, you perhaps have to boost that 3 orders of magnitude to be able to do that. And that's what those red bars are that are doing that. And so being able to control these things in the subsurface is of some importance. Aside, but maybe, the new hot topic, not so hot. This is 2003, the one hydrogen station that existed in Reykjavik, Iceland, for the Icelanders to use geothermal energy and hydropower through electrolysis to generate hydrogen to use as a battery in their fishing fleets and also in production. A big push at that time. Now it's back with us. Hydrogen and its production as a battery is thought of as an interesting way of storing renewable power, but also as a raw fuel. Hydrogen has been found as native hydrogen in Malawi and also is being sought for in the US. And the prospect to be able to create hydrogen, so-called orange hydrogen, by pumping water into hot iron-rich rocks is something that's being invested, so-called iron-rich intrusion, shown on the right here. The fact that you could inject water at depth into iron-rich rocks and catalyze a reaction involving hydrogen and recover the hydrogen is something that also requires that we make permeability, sustain permeability, and understand how that is done by injecting fluids into the subsurface. So triggered seismicity has been something that's been apparent in the US since the early 2000s with the shale gas revolution. It was really as a result of re-injecting fluids that were used to hydraulically frack the subsurface. Flowback would be recovered from those fractured wells, and those had to be disposed of. Sometimes they were disposed of in subsurface aquifers, non-potable water. And from that, they had created earthquakes in the Midwest and also in the Western Canada, in Western Alberta, in the foothills of the Rockies. We understand how it occurs. You inject fluids, you reduce effective stress, you reduce the strength of the rock across faults slip, and they may slip dynamically. Certainly in some cases where you want to stimulate reservoirs, such as this deep reservoir in South Korea, the Pohang Reservoir, you inject fluids to be able to dilate fractures and create a volumetric zone which has increased permeability for you to be able to circulate fluids to gain heat and to carry it up as a big geological heat exchanger to the surface. And during the stimulation of this particular reservoir, magnitude 5.5 earthquake occurred when none had occurred before in recent history, and was almost certainly due to this injection. So that essentially killed the project. And it is still dead from 2017. But the outcome of this was that the event that occurred turned out to be much larger than you'd have predicted based on the volume of fluid that was injected. And so the question arises as to whether, if the conditions that promote that, what they are exactly. And one postulate is that by having pre-existing tectonic stresses that are quite high in shear, the fault is primed, ready to go, and by injecting a relatively small amount of fluid that only raises the fluid pressure a small amount to reduce stress, to reduce strength a small amount, that's enough for it to fail. And that was basically what happened. We ran some experiments to see if that was the case. Story is, I guess, if you look at the Pohang event itself, the amount of fluid that was injected to get that relatively large energetic earthquake, the seismic moment being a measure of the energy that is released during the slipping. You can do experiments on laboratory faults by injecting fluids into them, and you can test the hypothesis that indeed pre-stressing a laboratory fault before you inject fluids into it is also a way to be able to generate a much larger event for a smaller injection volume, just as we anticipate or hypothesize happened in Pohang and was the reason for this big offset for the energy relative to the volume injected. And so the difference in volumes injected is something like 14 orders of magnitude, I think, 14 orders of magnitude. And the scaling 1-to-1 is also the same. And indeed, you can look at these behaviors in the lab experiments, and they bear out the fact that we can indeed do that. So we can understand something about the generation of events and how those are controlled by the magnitudes of the pre-existing stresses. So these events tend to be relatively large. The largest induced earthquakes in the US have been bordering on magnitude 6. The devastating earthquake in Myanmar 2 weeks ago, a week and a half ago, was of the order of 7.7. So they are relatively large events. You can only get these large events on relatively large faults. You can't get a very big event on a small fault. And so these large faults have the prospect to transect cap rocks, which might keep CO2 in place. And so they are a hazard in being able to allow fluids to be released to the surface. And the reactivation of faults occurs in two flavors. They occur as the regular earthquakes, which we see on plate boundaries and due to injections. And they also occur as silent or slow earthquakes, where the same energy is released, but they happen maybe instead of over 90 seconds or 2 minutes, they happen over 2 months. And so their effects are not felt in the same way that fast earthquakes are occurring. And so the question is, why do we get these two different behaviors for essentially the same loading? And you can define it in terms of the behavior of the change in strength that occurs with the straining of the rocks or reactivation on the fault. So the fault can either become weaker or stronger as it displaces, And if it becomes stronger, it self-arrests and nothing happens. It's not a dynamic event. And if it weakens as it displaces, so-called strain or displacement weakening, then you'd expect it certainly can provide a dynamic impulse, an earthquake, so long as some other conditions are present, and that is that there's enough stored strain energy around it, and that the stiffness of the system supplying energy to the fault is sufficiently soft that it will dissipate that energy dynamically. And the parameter that controls this behavior is this so-called A minus B parameter, which is negative if it's velocity weakening and positive if it's velocity strengthening. And a velocity weakening behavior is absolutely a necessary and required condition if you are going to have dynamic failure. And so it's possible that we could use this parameter, velocity strengthening or velocity weakening, which is a key failure behavior that's present on faults, to be able to index whether permeabilities on fractures will increase as they fail, as in dynamic failure, or decrease as they fail, as in creek closures you might get in these two styles of individual earthquakes. So we can test that hypothesis by measuring the behavior in the laboratory as to whether faults fail velocity weakening, which would be on the left-hand side of this plot, or in velocity strengthening, which would be on the right side of this plot, relative to the blue line. Ductile behavior, velocity strengthening; brittle behavior, velocity weakening. And one hypothesis might be that if it's failing in a ductile manner, it's destroying porosity as soon as it creates it, and therefore permeability would not increase, and you'd expect to fill this lower quadrant here. And if you have dynamic failure where you're creating porosity and permeability faster than you can destroy it, then you would populate this upper quadrant here. So that seems to work somewhat. It's not very clear. You get lots of false positives, I suppose. Of these rocks, actually, the schist is the Pullman schist from surf. The other ones are others from various places around the world. We'll talk more about a forge project today, another demonstration project. And if you do the same kinds of thing for the gneisses and the granites that are present at this geothermal demonstration project in Utah, you get similar behaviors that you populate these upper left quadrant. You're missing stuff in the lower right quadrant here. And if you look at these two plots combined, then you see some pattern, but it's again, it's quite diffuse, and there's also lots of false positives that would not allow you to use that generic. So that's not altogether entirely appealing. So maybe there's a way for us to be able to use field data from projects such as SURF at SURF, EGS Collab, and the Forge project to be able to say something about whether you can predict magnitudes of permeability change directly from measurements of the seismicity. And so around, I think, 2016, 2017, the EGS Collab, the Enhanced Geothermal Systems Collaboration Experiment, took place at the 4850 level at SURF. The idea, as we mentioned before, is to have an injection borehole and a recovery borehole drilled from one of the adits, shown in gray here. Have a fan of boreholes that were used for instrumentation, for seismometers, and electrical resistance tomography, and to basically inject water into the injection hole and measure its effect as it attempted to break through by reactivating fractures, causing small earthquakes, and to finally turn up in the recovery hole, and to understand the processes by which that is done. And so this Packer instrument was used that Yves Guglielmi has popularized, where you pack off a zone that you can elevate fluid pressures to fail a small fault and then measure the displacements that occur on that fault. And at this particular site, we have the two things that we'd like to have to be able to make a link between permeability and seismicity. You'd like to measure the time evolution of permeability, and at the same time, you'd like to record the seismicity that may be instrumental in that permeability change. And there aren't very many sites where that occurs. Lots of sites where you have seismicity, but not so many sites where you have concurrently measured permeability. So in this particular experiment, fluid was injected. The pressures were slowly increased, this red line here. And as a function of that increase, there was an increase in volume of fluid that was injected into the boreholes. And so if you have an injection volume that's recorded as a function of pressure that's injecting it, you have the potential to be able to recover from that the permeability and to use that permeability with the seismicity record in some smart way, maybe using machine learning to be able to potentially look for connections between those two. So you need those two guys. So this is the workflow. This is a view of the injection borehole and the seismicity that occurred around it. If we have a time history of both injection pressure and the flow rates that injection pressure caused, we can take the ratio of those to get the injectivity, which is a proxy measurement for the permeability, but it doesn't have a geometry of the injection included in it. If we look at the seismicity and choose an inner pressure boundary and an outer pressure boundary governed by that seismicity, the external limits of the seismicity is the external pressure boundary. We can use solve the differential equations for fluid flow to be able, with this outer boundary to defined, to be able to recover from those data a continuous log of permeability change over the duration of the experiment. And at the same time, in red here, we have the seismicity rate, and in black, we have the cumulative seismic magnitude, seismic moment recorded through these events as well. So we have some indicators of permeability evolution. We have permeability evolution. We have indicators of seismicity, and we can use the features of that to be able to run through this workflow, to be able to do that for all the different injection events we had. At EGS, they ran 5 different experiments. Nothing much happened in episodes 1 and 2, but in 3, 4, and 5 that are shown here, there was enough of a signal between permeability and seismicity that it was useful. And so what you can do is you can use the recorded magnitudes of the evolution of permeability with the observations of different metrics of seismicity, location, magnitude, and rate to see what might best fit in matching the data. So use some machine learning scheme to match the two together. And you run training between the observed raw data of permeability and the prediction of that permeability recovered from the seismicity in blue here. You look at evaluating it, and you look at testing it for unseen magnitudes of the permeability, and you find that you get a reasonable prediction that doesn't match over the full time history, but actually does a reasonable job of matching between the beginning and the changes in permeability at the final stages. You can, so that's reasonably successful. We see that there's a one-to-one relationship between the cumulative seismic moment and the evolution permeability, which is curious. We can do that on other sites. We have this other site where we're not 10 meters away from the injection, but we are something like 8,000 feet from it, from the surface, where there's an injection into the subsurface. Exactly the same process, injecting fluids into the subsurface to create permeability at 3 different locations along the deep well, and using 3 different stimulation techniques, just using water, I think in stage 1, using polymer and propellant in stage 2, and I forget what stage 3 was. So 3 different locations and 3 different forms of stimulation. We have the same data we had before, volumetric flow rates and pressures driving those flow rates together with the seismicity. We can use exactly the same workflow as before, in that we try and take the injectivity and convert that into a permeability history over time, the same time over which we have the seismic records that describe the attributes of the seismicity, location, magnitudes, and rates, and then do the same process for, in this case, the 3 episodes that we have to be able to look at those behaviors and use those to both train, evaluate, and test the data. And again, for the raw predictions of permeabilities, the red curves, we get a reasonable match from the predicted magnitudes of permeability changes, where we only use the observed seismicity to make those predictions. So we're able to do the same thing. And we see again that permeability scales directly with the cumulative seismic moment as the best indicator of what's going on in the subsurface. So that's interesting. So it means that we could use this technique to be able to pull that out. But more interesting, perhaps, is understanding the universality of it, whether you can do it everywhere. We have 2 sites where it's apparently worked. And also what it says about the mechanisms that are invoked to be able to link those 2 seemingly very disparate parameters together to be able to understand why it works. And so we could take the predictions using the Forge model and take the EGS collab data and try and predict the EGS collab data from those previous calibrations, if you like, using the Forge data. And if we do that, we tend to be able to predict the EGS data quite well for unseen permeabilities just using the Forge data, so-called transfer learning. If we turn the tables and do the opposite, calibrate the model with the collab data, and then use it with the Forge data to be able to predict the Forge permeabilities just from the Forge seismicity, we again get a similarly not bad result in terms of being able to predict the end magnitudes of permeability. So it seems to have some universality that using the data from one location allows you to calibrate models and mechanistically get the same results in the other location. So the question is why? So we note that the permeability scales with the cumulative seismic moment. We know that in these experiments in the field, such as at EGS Collab, with the injection and reactivation on faults, normal displacements and shear displacements on the fault were measured. And we talked about laboratory experiments where we looked at reactivation of laboratory faults and measured behaviors. We see the characteristics are that as you slip a fault and the displacement in shear increases, the aperture of the fault opens as it dilates over the roughness of that fault. It doesn't plow through those rough asperities, but it dilates over the top of them, and the fault gets, or the fracture gets wider. And so it seems that there's an intrinsic behavior that in slipping, we generate porosity in the fracture, and that porosity translates to a permeability. And so if you want to be able to link the physics of this, then one way is if you can link the permeability to the aperture of the individual fractures which cause that permeability. If you can link on a slipping fault the magnitude of the change in the aperture that occurs with the shear offset that occurs on that rough surface in a deterministic way through this. And if you can also link the size of the individual event that occurs to the magnitude of the shear offset through the shear modulus in the area of the fault, then you have a way of being able to link the magnitude of the event to the shear displacement to the change in aperture, and the change in aperture into a change in permeability. So that's basically the workflow, if you like, that allows you to get these behaviors that come out of it. And I think that's it. Yeah, so that's it. So I saw my 30-minute time just disappeared. And so basically the idea is that we'd like to be able to link seismicity to permeability as a predictive tool. We're not quite sure of the relationships, but it seems that from using machine learning that there is a direct linkage in at least 2 field projects that we've mentioned here that links the magnitude of the cumulative seismic moment to the changes in permeability that result from these reactivation of fractures. We've tried it at other underground research labs. The Bedretto site in Switzerland allows exactly the same conclusions to be drawn, and perhaps with better constraints on the final permeabilities, and that we can provide some mechanism by which that might occur. So it's great that I got involved in SURF 20 some years ago. I never at that time envisaged that I would be involved in these projects to look at linking seismicity to permeability changes. But it seems that it's a great facility that allows us to basically do that. And I should stop talking now and leave it open for questions if there are any. Thanks very much. Sure.
Right. Thanks a lot. That was very comprehensive. So let's see if we have any questions from the audience. And I've been new to this, so I'm also like looking at my various open. Oh yes, Steve Secula. I assume I can just.
Yes.
Yeah, can you hear okay?
I
Yeah.
can hear them.
Yeah, so we're joining from Snow Lab and we have a question from the audience.
Hi, that was a really good, interesting talk. Thanks for the talk. I just have a question, like, just curious to know, when you do these studies for seismicities and everything, so with this induced seismicity, have you done any studies on the changes in the radioactivity? Like how much
Changes in what? I missed the last studies on changes in what?
radioactivity? How much it increases the radioactivity every time?
No, we haven't. I guess are you a physicist worried about how radioactivity changes with reactivation? We haven't measured you said radioactivity, right?
Yes.
Did you say yes?
Yeah, it's radioactivity. It changes in radioactivity with the changes in seismicity, permeability, etc.
Yeah, no, I don't think they were measured at EGS. If there's anyone online from EGS collab experiment who knows otherwise, then chirp up. But I don't imagine that was necessarily something that was measured.
Okay, thank you.
So it can't be correlated. So there's two people with hands up. I see Tom. The first was Stephen Secula. Was that the question I answered?
Yep.
Tom, is that your question that's online that I see?
Yeah, I don't mind stating it orally though, but yeah, that's my question. I didn't know.
It's very small on my screen.
Yeah, so am I up or is somebody else ahead of me?
I think you're up. Stephen,
okay.
hold your
Yeah,
hand.
it was a great talk. I love this. So, but going back, you're using basically specific capacity or Q over P as your measure of permeability. And I think you noted correctly that that depends on a lot of geometry things, and it's especially very, very sensitive to what's happening very close to the borehole. In one case, or it can be very sensitive to what's happening at the outer boundary if it's a closed system. So I'm just trying to explore. It sounds like you're already thinking about seeing if there's some better ways, some better measures of permeability than just injectivity or productivity. And I'm just wondering what some of those might be. Maybe for something that's longer lasting, could you, for example, use, if you had some earth tide effects, could use those to get a diffusivity measure? So I'm just want to explore this, a wonderful thing, but I'm just want to explore that particular question, because that could account for a lot of the discrepancies and difficulty in training, or not difficulty in training, you train very well, but that could account for some of the discrepancies that permeability measure itself has some wonkiness to it.
Yeah, so our assumptions, Tom, are that we treat it as an equivalent spherical or radial permeability that's uniform, which of course isn't, because you're picking off these individual fractures. We assume that there's no storage in the system, that it's a whole sequence of steady states, which of course is simplification that we choose to make to do this. We only have we have a couple of other independent views of this. The other independent views I didn't talk about today are twofold. One is that we've done the same thing in the laboratory, stimulating laboratory fault to slip and to measure incrementally the AEs, calibrated AEs, and link it to permeability, and we get the same results. But now, of course, we can measure permeability changes steady state directly because we have control of that. And the same linkage between permeability change and cumulative seismic moments seems to hold. We can also look on the laboratory faults and see what the sizes of the nucleating patches are from the signals, and those are smaller than the individual faults. And within a single stimulation for a single pressure step, we maybe get 100 of these events, all of which are maybe less than 1/10 of the area of the fault. So what we think is happening is that these patches are slowly firing off and ultimately covering the whole fault during the time of the cumulative events that occur. And it's these that give some structure to the increase in permeability on the fault. So that's one of the things that we've tried to do that avoids the difficulties of the systems with converging flow around boreholes and fractures not intersecting very nicely the borehole itself. The other thing that we've tried to do is with the Bedretto lab in Switzerland, where they have independent measurements of permeability at the end of the experiments. And so we've done exactly the same thing. These fault figures are the same. I didn't include this in the presentation, but on the top left side are magnitudes of the predictions of permeability from the end magnitude of permeabilities for all the zones in which they did the stimulations. The permeabilities on the right-hand side are the predictions from using the seismicity. And the measurements at the left-hand side are when you've dropped the pressure. And so one other problem with our measurements is that we're recording the permeabilities just due to the nature of our experiments at the peak pressure, which is underway at the end of the test before that pressure goes to zero. That's the permeability we predict from the seismicity. And of course, that isn't the same as the permeability that you measure once you bleed off that pressure and you're at background pressures, and you do a pump test then under a relatively small incremented pressure to be able to measure that. So we see that they're of similar magnitudes, but they differ. But they have some kind of structure in that they all revert to the other pressure by declining along the same approximate pressure versus permeability curve in log pressure, log permeability space. So yeah, we have tried to measure this in other ways in the laboratory. We have tried to confirm these magnitudes for permeability in other ways by using field tests where those are quite meticulously measured. And we seem to get similar results. And we realize that this is kind of an order of magnitude exercise that links these things, not to within factors of decimals, perhaps bigger than a factor of 2 of the actual magnitudes, but those are the attempts that we've tried to do for that.
All right, thanks. And we have another question from Jeff Burkhardt. I don't know if he wants to talk out loud or if I should just read his question.
Is it chat?
Yeah, so it's about the permeability from EGS collab that was strengthened and that it depended on fluid pressure to keep the fractures open. And the fluid pressure went down, the permeability decreased again. While with Forge, they have proppants, the permeability remains. Now he moved it, remains. And then if this difference was accounted for in the conceptual model.
Yeah, that's Jeff's comment, I think. And he says
Yes.
he can't speak. Can you not speak, Jeff? Okay, I'll take that.
Oh, it looks like maybe I just figured
there
out.
you go.
Hear me?
No, I understand your question. I think much of your question may have been answered in
Yeah,
response
right.
to Tom.
Yeah, I think you already answered it. So thanks.
And that would basically be my question too, in terms of like, are you planning to do that with EGS experiment 3 here at SURF, right? Then using propants and
You'd have to ask Jeff that. So I know that Collab 2.0 is that still live, or is that I'm talking to you, conversation, Jeff, is that still live, or has that been affected in the machinations of the federal government at present?
So the cusp is still alive, and it's still in our list of aspirations. Budget to do it still pending. So yeah.
Good, great. Cool. This would be an interesting thing to do there. Also.
All right, excellent. I think I don't see any more. Oh, no, there's a question from Mike Ray about limiting the concerns of underground stresses on major faults when it comes to the goal of placing enhanced geothermal anywhere on the planet. How much could this concern limit the potential for enhanced geothermal?
Is that question here? I was looking for it. Do you want to restate it, Marcus?
It's in the Q&A. So how limiting are the concerns over underground stresses on major faults when it comes to the goal of placing enhanced geothermal anywhere on the planet? And how much could this concern limit the potential for enhanced geothermal?
I think it does. It's already limited at both Basel and Pohang to sites that will never be resurrected, I think, because of this exact problem. But there are sites that are survived and continue to survive with low levels of seismicity, like Sulz in France on the Rhine Graben. And so it seems that structure and local conditions are everything that control this. Plus, I think the paradigm of EGS as a attempting to do hydroshear and to create a volumetric reservoir have been, I would say, slightly upended by the idea, which has been quite successfully prosecuted through horizontal drilling and massive hydraulic fracturing at Fervo's sites, that you can actually maybe just completely stimulate the reservoir using conventional oil and gas techniques, use propellants, and then not worry so much about the previous worry was that you develop these short-circuiting pathways that give you a cold short circuit and kill your reservoir in terms of heat transport. And so I guess the succinct response to your question is yes, structure and stresses matter where these are done. There seem to be methods of doing this that might overcome the sensitivity of some of these sites in terms of that respect as well.
All right, and we have one more question on safety. So what are some on-site safety risk management systems used when working with high pressure experiments?
Well, since I didn't set foot at SURF during the EGS collab, I'm the wrong person to ask that of. But I think the normal constraints you'd have in the lab in working with high fluid pressures. These fluids are liquids, and therefore high pressures doesn't necessarily transmit into high pressure gases, which are much more compressible and therefore much more explosive.
Yeah.
Say, but that's all I could add to that statement, to that comment.
All right, thanks a lot. And with that, do I see anything else? Not really. So thank you again, Derek. Great talk. And as usual, I have some final comments in terms of like that this talk is available to view and share on YouTube, Vimeo, and as I mentioned earlier, on institute.surf/deeper-talks webpage. And next month's Deeper Talk will be on May 14, same time, 9 o'clock in Mountain Time. And the topic is underground operations, maintaining lab facilities beyond the 4850 level. With the featured speaker, Bryce Peitzek, our underground operations director, and Jason Conant. And as always, your feedback helps improve this program, and we appreciate any suggestions for speakers and topics for future talks. And please fill out the short survey you will receive immediately following the talk on Zoom and in your email.
That's a lot of instructions. Thanks very much, everybody, who turned up and who participated. Great. Thanks again.
Thanks a lot, Derek. And
Bye.
thanks a lot, everybody who's joining with that. Talk to you. See you all again next month.
Take care.
Thanks. Bye.